aspects of SYZ. There's a link on our website from which you should be able to access the Zoom links, so that we won't be using our usual Zoom links and we won't be at the usual Zoom times, but we'll have those activities Tuesday through Friday, and Friday in particular in place of our seminar. So with all that said, without further ado, it's our pleasure to have Jonny Evans today from Lancaster University, who will tell us about, I believe, a Lagrangian Klein bottle you can't squeeze.
Sounds about right, yeah. Should I share my screen now?
Yes.
If I do that, will it just, yeah, okay, there we go. Share screen. Okay, can you see my screen?
Looks great.
And you can hear me okay? So, very good. Well, thank you very much for the invitation. And I'd also just like to say thank you very much to the organisers for organising this seminar series, full stop, because I think it's wonderful. Like, shortly after the UK went into lockdown, the first of these happened, and it was just really nice to have, 250 names I recognised in a list on a screen, all watching the same thing, and it was a really nice experience. I've realised that with my screen share, because I'm not used to Zoom, I can't see the entire of my screen. Is there any way of hiding the little thing on the right-hand side with my face and Shield's face? Do you know? Maybe if I click this. No. Oh, there we go. It's gone. Okay, cool. So yeah, I want to talk about a Lagrangian Klein bottle that you can't squeeze. So let me explain the motivating problem that led me to think about this. So you're given a symplectic four manifold X omega and a non-orientable Lagrangian surface inside X. So I'll talk a bit about why non-orientable in a second. So the question is, how far can you deform the symplectic form omega in cohomology before you find that there's no Lagrangian either smoothly isotopic to L or maybe in the same Z mod 2, that's supposed to be a Z mod 2 homology class as L. In other words, how far can you deform omega before L disappears? So for a start, why am I focusing on non-orientable things here? Well, the analogous question with orientable Lagrangians is maybe a bit easier, because there's this constraint that if L is orientable, then you can integrate omega over L, and you've got to get 0. So at least if L has a non-trivial homology class, this is a non-trivial constraint on the cohomology class of omega. So you have to deform amongst such homology classes in order for L to remain Lagrangian. I guess another question along the same lines is, if you fix class beta in the second homology with Z mod 2 coefficients, you can ask what is the minimal non-orientable genus of a Lagrangian in beta. So that's a related question, right? So if you're asking, how far can you deform omega to keep the same L, maybe the genus has to increase as you deform omega. And again, this question is more interesting for non-orientable things than it is for orientable things, because for orientable things, we know that the Euler characteristic of L equals minus L squared, as in minus the cohomology class of L squared. So that tells us what the genus is, whereas for non-orientable things, this is not quite true anymore. So I can't see anybody, and I can't see any chat. So do let me know if you can't see what I'm writing, or if anything goes wrong, because I won't know otherwise. Just be talking to the void. Okay, so let me tell you a bit about non-orientable Lagrangians, because I don't know, non-orientable things, often people don't really think about them. You would always assume something's orientable. So here's some stuff, some facts about non-orientable Lagrangians. So, so first, what's the analogous statement to this chi L equals minus L squared? Well, there is something you can say. So this is due to Audin, I think, which is that maybe you can't specify exactly what the Euler characteristic of L is, but it's going to be equal to not quite the square of L, but the Polterovich square of the homology class of L, which I was calling beta. So this is, so if you have a Z mod 2 homology class and you square it, that's just going to give you a Z mod 2 homology class, but you can do slightly better than that and actually find a Z mod 4 homology class called the Polterovich square. Sorry, this is in H0x with Z mod 4 coefficients, I guess. So this tells you basically that this is equality modulo 4. So you don't know what the minimal non-orientable genus is, but maybe you know that the genus modulo 4. So remember, any non-orientable surface is some connect sum of RP2s, and the Euler characteristic is 2 minus the number of RP2 factors. So we're saying that is equal to beta squared. Okay, so let me just do an example. So I want to do X is S2 times S2. So how many, because I can't see or hear anyone, I want a bit of audience participation. How many Z mod 2 homology classes are there in X? What is H2 of X? Shout out the answer. If no one shouts, I know my internet's gone. I can't hear anyone. Is the reason I can't hear anyone because the internet's gone, or is it because everyone's shy?
I think we're all afraid of saying the wrong thing.
Still like, no one's saying anything.
We can hear you
there are
fine.
4 classes. Say again?
We can hear you.
You can hear me, fantastic. Well, the answer is there are 4 classes, right? The cohomology is Z mod 2 times Z mod 2. So there are 4 elements. So there's 0, 0, there's 1, 0, there's 0, 1, and there's 1, 1. Okay, so let's deal with these 4 cases separately. And I also need to tell you which symplectic form I'm talking about. I'm talking about, actually, maybe I'll just make a bit of space. I'm talking about the symplectic form, sort of P1 star sigma plus lambda P2 star sigma. So sigma is the area form on S2 with area 1. So we're giving the first factor area 1, the second factor area lambda. I may decide to switch the lambda to the first factor later. Okay, so what is the minimal genus, non-orientable genus of a Lagrangian that is null homologous? Well, is it possible to have a null homologous Klein bottle? Turns out no, because there's a theorem of Schiff-Shishin, and another independent proof by Nemirovsky that says there's no Lagrangian Klein bottle that's null homologous in any sort of rational four manifold. So the minimal non-orientable genus therefore is 6, right? Because it has to be equal to what does that have to be? So chi has to be equal to 0 mod 4. So 2 minus the number of RP2s has to be equal to 0 mod 4. And you can get a surface of genus 6. So Givental constructed one inside the four ball. So you just stick that inside any four manifold you want. Okay, let's look at the other homology classes. So I'm going to draw a picture of S2 times S2 now, the toric picture. And I guess I got the lambda on the wrong factor. I want the lambda to be over here. So this is a rectangle with height 1 and base lambda. In these toric pictures, the length of an edge is the symplectic area of the corresponding sphere. So this horizontal one is lambda. Okay, so let's look at the class 0, 1 first. So I claim that there is a Lagrangian Klein bottle in this class, and I can also draw a picture of that. So here's a picture of the Klein bottle. It's this blue line. So this line has slope 2. So what I'm drawing here is the projection of a Lagrangian Klein bottle to the moment polytope via the moment map. So how do I know there's a Klein bottle there? Well, remember the fibers of the moment map are tori, so let me draw a torus. That's the fiber.
Johnny, there's a question from Ailsa.
Oh, sorry, yes, go
Ailsa,
ahead.
go ahead.
Is Givental's construction, that's the one where you start with an immersion and then you resolve double points in that paper that's mostly about immersions?
I think technically in his paper you just draw a front projection or something and then turn it into a Lagrangian, but I've forgotten. It's quite a short paper. Mm-hmm. Yeah, it's quite possible that he draws some immersed Lagrangian and then resolves the double points. I've forgotten exactly.
Okay, yeah. That's okay, thanks.
Okay, yeah, but it's very explicit anyway. I mean, it's also possible to draw one of these tropical pictures of this Genus 6 thing. So I'll draw some of those later. Let me just make this torus a bit bigger. So here's the torus that's the fiber of the moment map. And so what I'm going to do is I'm going to draw in this torus the circle where this Lagrangian Klein bottle intersects this fiber. Okay, so the Klein bottle is 2-dimensional, so its projection is 1-dimensional, so the fibers of the projection should be 1-dimensional, and they are the lines with slope -0.5. Okay, so that's a circle in the fiber. This is slope -0.5. And basically, if you take coordinates in the base, like let's say P1 and P2, and coordinates in the fiber, θ1, θ2, these are action angle coordinates. So the symplectic form is really dP1 wedged θ1 plus dP2 wedged θ2. And the fact that the slopes are 2 and -0.5 is exactly what tells you that this thing is Lagrangian, this blue thing. And how do you know it's a Klein bottle? Well, over the interior of this interval I've drawn, this blue interval, it's an annulus. And as you move to the boundary, what happens is that annulus collapses onto the θ1 circle, and that's 2 to 1. So it's like a Möbius strip, as in it's like the boundary of a Möbius strip collapsing onto the core of a Möbius strip. So the way I'm going to draw that in these pictures is I'm going to draw like a cross cap symbol over the 2 endpoints. So that's how you should think of this Klein bottle. It's 2 Möbius strips, 2 Lagrangian Möbius strips that sort of meet in the middle. Are there any questions? So this is what's called a visible Lagrangian. This kind of construction was first, at least as far as I know, first noticed by Symington in papers on almost toric manifolds. So it's called a visible Lagrangian. And it's since been generalized to allow sort of graphs instead of just straight lines. Those are the tropical Lagrangians that Matesi and Michalkin have constructed. But anyway, there's a Lagrangian Klein bottle. It lives in the class 0, 1. Well, we know it's not null homologous and it doesn't intersect this vertical sphere, so that's the only class it could live in. And that's this class here. So the minimal genus there is 2. It's 2 Klein bottle, the 2 RP2s. Let me now focus on this class, 1, 0. Okay, so let's try and do the same thing. I'm going to draw a line of slope a half. Straight line of slope a half. And Well, it depends, doesn't it? Right. So if this is a very, very wide rectangle, then that line of slope a half is going to hit the top edge rather than the side edge, and that's no good. So basically what goes wrong is if this is length 2 and this is length 1, then, you know, I run into problems. I can't draw this line because it's going to hit the corners. And that's no longer a Klein bottle. This thing is actually singular. It's got 2 singular points here and here. So this is a singular sphere. Okay, so here's the conjecture. The conjecture is that the minimal non-orientable genus of a Lagrangian in this class, which I'll call beta, that was 1, 0, wasn't it? Is greater than or equal to 6 if lambda is greater than or equal to 2. Right, so if your rectangle is too wide, you can't fit a Klein bottle. That's the conjecture. So you might ask, well, what can you fit? And the answer is, I don't know. Here's something you can fit, but maybe you can do better than this. So this is a challenge. Can you do better than this? So here's a rectangle, a very long rectangle. What I'm going to draw for you is a tropical curve in this rectangle, which will then, via Michalkin-Matesi tropical Lagrangian construction, give you a Lagrangian submanifold. It's going to be very high genus, but it should work. So let's see. I'll tell you what the slopes of these lines are because that's important. Okay, so this guy is pointing in the 2, -1 direction. This guy is pointing in the 3, 1 direction. And this guy is pointing in the 1, 2 direction. And then all the other ones are parallel to one of these. So I claim, oh, I've drawn that wrong, I believe. That's right now. Yeah, okay. So this doesn't run into the same kind of problems the one above does, because well, it eventually does, but what you can do is you can basically stretch your rectangle out until its side length is 12 before this one stops working. Because when the side length is 12, well, basically 2 plus 3 plus 2 plus 3 plus 2 is 12, I think. And that's when this thing starts hitting the corners of the rectangle and you can't draw this shape anymore. So I claim this thing is a Lagrangian, which is non-orientable and has genus 22. So for an even longer rectangle, you'd have to increase the genus still further. So my conjecture about this is that actually eventually you should actually be able to get an upper bound on the genus even as you increase the rectangle. That would be my guess, but I don't know. So I can't prove any of these things yet. So let me tell you what I can actually prove. Just before I do, are there any questions?
Hi, Johnny. Yes, I had a question. This is Sheil. I just was wondering, so I just want to clarify the last thing you said. So would you conjecture that as lambda keeps growing, the minimal genus keeps increasing by like some precise value, or it's not quite that
No,
clear?
my guess would be exactly the opposite. That as you start increasing lambda, eventually you can always fit anything in. Sorry, as in the minimal genus should be bounded as you increase lambda. That would be my guess. Because somehow we've got tools for proving things about there's no Klein bottle, there's no RP2. We don't have any tools for proving, as far as I know, we don't have any tools for ruling out the existence of non-monotone or non-exact high genus non-orientable things. They're just too icky. Like I just imagine that probably at some point for very large lambda, some H principle will kick in to be able to construct Lagrangians of relatively low genus. That would be my guess. But I also think they won't come from these tropical pictures. I think this is probably as good as you can get with tropical Lagrangians. Sorry, maybe you said something else. I didn't hear.
Oh, no, thanks. That clarifies. Thanks.
Yeah, I don't have any reason for believing that, except that I think it'd be easy to prove that than it would be to prove the opposite, that lambda that the genus grows as lambda grows. Okay, so let me tell you what I can actually prove. So it's inspired by this first conjecture, but it's not as much as the first conjecture. Okay, so here's a toric picture. But I'm not including the top boundary, I'm not including the bottom boundary. So it's kind of an open toric manifold. But it's an open toric manifold where this height is really 1 and this length here is lambda. So let's call this manifold maybe U lambda. So what is this? This is a sphere in this direction with area lambda, and in this vertical direction, it's an annulus, a sort of open annulus. So the theorem is, if I have an embedding of the Klein bottle into U lambda, which is Lagrangian, then if lambda is bigger than 2, I guess bigger than or equal to, because I've cut the top and bottom off, then the map I star on homology, this is first homology with rational coefficients from the Klein bottle into the ambient manifold, is an isomorphism. Is 0. So this map is, there's only 2 things this map could be. It could be 0 or it could be an isomorphism. I often get them mixed up. So because the first homology of the Klein bottle is like Z plus Z mod 2. So when you take it with Q coefficients, it's just Q. And the first homology of this thing, well, the S2 factor is simply connected and this vertical factor is just a circle. So it's Q. So it's a map, it's either 0 or it's an isomorphism. And let me check my notes. It's 0, yeah. So the claim is it's 0. And for the Klein bottle that I drew earlier on, this map is an isomorphism. So let's just, for example, if we make this 1 slightly longer, so that we actually can fit the Klein bottle in, this Klein bottle here, then the claim is for this guy, I star is an isomorphism. And you can see that because what is the generator of the first homology of U lambda? It's this circle here, which is the fiber over a point in this boundary. And what is the generator of the first homology of the Klein bottle? It's this core of this Möbius strip that is exactly the same as that circle over there. So, you know, literally they're the same circle. So you get an isomorphism here. And that means this Klein bottle can't be squeezed into too small a region. In other words, you can't sort of shrink this height less than half of the width. Because if you do, your Klein bottle won't come with you. Okay, so that's the statement of the theorem. Are there any questions about that? Okay, so I hopefully will have time to prove this. So the proof is sort of neck stretching SFT style argument. Okay, so here's how I'm going to prove it. I'm going to assume not. You probably don't have to phrase it in this way, but I'm going to assume that there is a Klein bottle, a Lagrangian Klein bottle, with I star an isomorphism, and lambda bigger than or equal to 2, and we'll get a contradiction. So
can I just ask?
Here's what we do. Yeah.
I'm just slightly confused. So in the theorem, does it not follow from Shevchishin's result that then there just is no Lagrangian Klein bottle in that?
No,
class?
because it's for this particular Klein bottle, I star is an isomorphism, so you can't squeeze it in. But you could imagine having a Klein bottle inside this U lambda for which I star was an isomorphism. Sorry, was 0. That's not something I can rule out.
Okay, that's not. So
our
that's not
favorite
ruled
Klein
out.
bottle. That's not ruled out by the theorem. Our favorite Klein bottle doesn't have that property, so we can't squeeze it. But you could imagine having another Klein bottle that for which this map is 0.
I see.
I imagine that's actually not possible, but I can't prove it. Basically, the problem is these two spheres. So, if you put these two spheres back in the top and the bottom sphere, so you're back in S2 times S2, to reduce the previous conjecture to this theorem, you'd have to produce a pair of symplectic spheres that kind of link your Klein bottle in exactly the right way so that they're disjoint from the Klein bottle and such that this map is an isomorphism. And if you try and prove that kind of statement using SFT and neck stretching, you run into problems. And these are the kind of problems that people had when they tried to use SFT to prove that there's no null homologous Klein bottle. They sort of threading the needle type of constructions. So I think it's actually, this conjecture on the previous page, I think, is quite hard, as in I can't prove it. So, but maybe, I talked to Gyugyos and he claimed he couldn't prove it either, so it must be hard. Okay, so let's assume there's a Klein bottle such this map is an isomorphism, and the width is sufficiently large that it shouldn't be there. So what I'm going to do is I'm going to stick those two spheres back in again. So how do I do that? Well, actually, let me do it like this. I've got my Klein bottle in the complement of these two spheres in U lambda. So that's just going to be some kind of messy thing. And then I'm going to symplectically cut at the top and the bottom. So I reintroduce these two spheres. And that doesn't affect my Klein bottle because my Klein bottle's inside the interior of this manifold. So let me give those spheres a name. I'm going to call this one S1 and this one S0. Okay, that's the first thing. Then what am I going to do? I'm going to pick an almost complex structure. And it's going to have the following properties. So such that, well, it's going to be a neck stretching almost complex structure. So let me redraw the manifold in the following way. There's a top bit, a neck, and a bottom bit. So the bottom bit is a neighborhood of the Lagrangian Klein bottle. So the top bit is a neighborhood of, well, it's something that contains these two spheres. It's the complement of the Klein bottle. And then there's a neck in between. So J plus on the complement has the property that S1 and S0 are J holomorphic. J minus on the bottom is going to be a particular almost complex structure constructed by Monke, Klaus Monke, which I'll talk more about when it becomes important. And in the middle, this is just a neck stretch. In other words, it's some sort of sort of vertically translation invariant, almost complex structure that I can stretch. And then I'm going to stretch the neck. So I get a sequence of almost complex structures, JT, which agree with J plus at the top, they agree with J minus at the bottom, and in between, they agree with this translationally invariant almost complex structure over a longer and longer region. So that's what it means to do neck stretching. Okay, so what am I going to do? I'm going to fix a point X in my Klein bottle. I'll probably alternate between calling this K and L because it's a Klein bottle and it's Lagrangian, and I can't keep track of which letter I've used. So I'm going to fix a point X in the Klein bottle, and I'm going to look at UT, which is the unique J-holomorphic curve in this symplectic cut manifold, which I'll call X, S2 times S2, such that, so UT is J-holomorphic, let's say JT holomorphic. UT of 0 is going to live in S0, UT of 1 is going to live in S1, and UT of infinity is going to be the point X in the Klein bottle. So, and UT, I guess, lives in the homology class, which maybe I should call alpha. Which homology class is it? It's this vertical one. Okay, so this is my UT. It's the smaller of the two areas. So, you know, this vertical area is 1 and this horizontal area is 2. I can actually assume it's equal to 2 if lambda is strictly greater than 2. I can always add a bit more vertical space and assume that it's really twice as big as the height here. So that's the class alpha. I should write it like this. Okay, so what I'm going to do is I'm going to look at the behavior of UT as t goes to infinity, so as the neck gets very long, and derive a contradiction. So are there any questions? Okay. So here's the claim. Yeah. Well, actually, maybe before I say the claim, I should tell you what happens in the limit. I'm sure many of you have seen these kind of arguments before, but I should probably say it anyway. So as t goes to infinity, you get this kind of picture where the manifold breaks apart into some pieces. The bottom piece will be basically a copy of T star of the Klein bottle. The top piece will be the symplectic completion of the whatever you started with. And that turns out to be symplectomorphic to the complement of the Klein bottle. So I'm going to call it V. It's X minus the Klein bottle. And this bit in between is the symplectization of the unit tangent bundle of the Klein bottle. So your manifold splits apart into pieces. Maybe there are several of these symplectization regions, but they're not going to be the interesting bits. I'll just draw one of them. There's still going to be these J-holomorphic submanifolds at the top, and there's still going to be a Klein bottle down at the bottom. And our holomorphic curve U splits into pieces as well. Now, at all times, U had a point that lived in S0, it had a point that lived in S1, so the limit is going to have points where it hits those spheres as well. And it also had a point living on at X inside the Klein bottle, so it's going to have a limit point down here as well, a component of its limit. And these pieces are finite energy punctured holomorphic curves. They're asymptotic to Rabe orbits in the contact boundary. Okay, so what we need to do is we need to analyze these pieces and find something fishy about them. So here is what I claim is the fishy thing. Let me get the statement right. So in the SFT limit, there is a cylindrical component through X, which has odd homological intersection with the Klein bottle. So what do I mean? Well, this cylinder's going to have boundary off at infinity. The Klein bottle is a compact, okay, non-orientable, but compact thing. So they have a well-defined Z mod 2 intersection number. I'm claiming it's odd rather than even. And I claim this is dodgy because, so what Monka proved was for this particular J minus, this particular almost complex structure we're using, a generic X doesn't have this property. It doesn't live in a J minus holomorphic cylinder having odd intersection number with K. So the point is, we didn't really specify which X we're looking at. So this argument works for any X, but for a generic X, this is something we're not allowed to find at the end of the argument. So I'll prove this claim. Are there any questions about this argument?
Yes. Hi, Johnny. I just had a question about the statement. When you say cylindrical components, am I supposed to think there's just sort of two cylindrical ends going to Rabe orbits and then it's coming down and just crossing K in the cotangent bundle? Or
yeah, it's as in it looks like this.
Okay, great.
And
thanks.
that it passes through X. And maybe it hits the Klein bottle at other points as well, but you know, it hits at an odd number of points. That's the claim. Any other questions? Okay, so how do we prove this claim? Okay, so first of all, there's at least two components which are topologically disks or planes. So at least, people always say planes because they're sort of conformally planes. So at least two planar components of the limit. I say at least two. It could be that these two have the same geometric image, so they could be two planes mapping to the same thing. But there have to be at least two, basically for Euler characteristic reasons, because we're stretching a sphere that has Euler characteristic 2. In the limit, we have a bunch of punctured curves, all of which have at least one puncture, so they have an Euler characteristic at most 1. So you need at least 2 with Euler characteristic 1. And actually, the more punctures you have, the more planar components you're going to need in the limit to cap those off. So they could possibly have the same image. But we'll see that doesn't actually happen in the end. Moreover, there are no disks or no planes in T star K, Klein bottle, or in the neck. And that's just because their asymptotes have to be Rabe orbits, and with this particular choice of almost complex structure, you know, and contact form, the Rabe flow is the geodesic flow on the Klein bottle, and there are no contractible geodesics on the Klein bottle. And if you had a plane asymptotic to a contractible geodesic, you'd have a contraction. So if you have, you know what I mean? If you had a plane asymptotic to a geodesic, it would give you a contraction of the geodesic just by projecting back down to the zero section. So this is because there are no contractible geodesics on K. Okay, so that means all the planar components have to be up here in V. Let me redraw the limit. So we have to have sort of at least two planar components up at the top. Okay, next claim, subclaim. If a component in V, this top bit, doesn't pass through either of these spheres, then its area is at least 1. So what do I mean by area here? This is a non-compact thing. Well, it's non-compact, but it's actually symplectomorphic to X minus the Klein bottle if you equip it with a suitable symplectic form. So when you do these SFT next stretching arguments, what happens to the symplectic area of the curve you're stretching is it basically gets concentrated up at the top, and the sum of the symplectic areas of these components in V will be the symplectic area of the sphere you started with. And the symplectic form I'm using on V to make that statement true is the one for which it's really the complement to the Klein bottle. Okay, so why is that? So let's prove this first, and then I'll go on and explain how this helps. Well, if the curve misses both S0 and S1, then really it defines a class in the homology of U lambda, which, just whizzing back up again, U lambda was this non-compact thing where we cut out the top and the bottom spheres. Right, that's what I'm saying. If it misses both spheres, you can cut them out and you don't lose anything, but it's a relative homology class relative to the Lagrangian because it has boundary on the Lagrangian, as in it's asymptotic to a geodesic on the Lagrangian. Okay, and the claim is that these guys are going to have integral area. So how does this go? Let's look at the exact sequence of the pair U lambda K. The next term is H1K, the next term is H1 of U lambda, and the previous term is H2 of U lambda. This map we're assuming is an isomorphism, so this is where that assumption comes in. Maybe you'd forgotten about it. It's an isomorphism, so the exact sequence splits like this, and well, sorry, that's not quite true, isn't it? So we have to be careful about coefficients. It's an isomorphism rationally. This homology group is Z mod 2 plus Z. So what I'm saying is the Z maps isomorphically onto the Z over here. So we can ignore that. Okay, but then that's saying that this map here, this from Z to something to Z mod 2, it's either, this is either going to be Z or it's going to be Z plus Z mod 2 in the middle. And the symplectic area of the sort of non-trivial thing here is going to be either the same as the area of this guy or half the area of this guy. So maybe I should say this in a better way. So the area of a generator of infinite order, so a generator of the infinite order Z inside H2 of this relative group is either the area of a generator of H2 U lambda or half of that. Right, so if there's no Z mod 2 here, then you get exactly the area, but if what am I trying to say? If this group is index 2 inside this group, then this generator is going to have twice, have half the area. And what is the area of a generator of this group going up? It's 2, right? This is the generator of the second homology of U lambda, this horizontal line, and that has area 2, symplectic area 2. So that's what tells us that the this disk with boundary on K has to have area at least 1. Are there any questions about that? I feel like I fluffed up the argument there by saying lots of wrong things, but hopefully the final result was right. Is there any questions? Okay, so the outcome of this is if you have a SFT component that misses both of these two spheres, its area is at least 1. The curve we started with had area 1 because it's in this vertical homology class. So that means there couldn't be anything else. So if we stretched and found a component that had area 1, there wouldn't be room for any more components. But we know that there is a component that intersects S0 and a component that intersects S1, maybe the same component, but still there's something else. That means there's no component that misses S0 and S1. So that says all components, all components hit either S0 or S1. Okay. And there have to be 2 disks, right? We said that originally there has to be at least 2 planar components. And so there's only 2 possibilities now. First possibility is there are 2 disks, one that hits S0 and one that hits S1, and they have to hit exactly once with multiplicity 1 by positivity of intersections. The other possibility is you have a disk, a single disk, which hits both of them. But then that would, you know, you'd have to have 2 disks, so you'd have to have another disk that does the same thing. And now the intersection number of this with, let's say, S0 is 2, but the original curve you started with has intersection number 1, so this would be a contradiction. So this is the only thing that happens. So this is ruled out by positivity of intersections. It also shows you these disks are simple disks. There's no multiple covers because, again, that would increase the intersection number of these disks with S0 and S1. So we're really in this situation over here. So before I finish the proof, are there any questions? Okay, so this is really telling us there are only 2 components in the limit, and those 2 components are a disk and a disk. One hits S0 and one hits S1. So now, so this is the structure with these SFT proofs. You always control what's in the top first, and then you work your way down and see what's lower down. So what about in the neighborhood of the Klein bottle? Well, I claim that there can only be 1 component down here, and it has to be a cylinder. So why is that? Well, let's think if there were more than 1 component, or if the component had more than 1 and more than 2 boundaries, then we'd have to have more disks up here. And those disks would have to be disjoint from S0 and S1, or they'd increase the intersection number with those 2 spheres, and that's not allowed. So that can't happen, and there can only be 2 positive asymptotes coming from the bottom. So there has to be a cylinder at the bottom, and the cylinder has to have this odd intersection number with the Klein bottle because the curve we started with was in this Z-mod 2 homology class that has odd intersection number with the Klein bottle. So that gives us this cylinder, and also the cylinder passes through X. So by construction, because it's the limit of things that pass through X. That's a closed condition. So this produces the dodgy curve, dodgy cylinder, which Monka ruled out, or which generically doesn't exist for generic X. Okay, so that proves the claim, which is then a contradiction. So this map can't be an isomorphism. Okay, are there any questions?
I had one question. Can you remind again why there had to be 2 planar components?
Yeah, sure. That's because we were stretching a sphere. A sphere has Euler characteristic 2. The limit will have lots of punctured pieces, but nothing closed, right? Because we know that there's at least 3 components in the limit, or at least 2 components, let's say. So they all have to be punctured, and a punctured surface has Euler characteristic at most 1. So you need to have at least 2 components to add up to the Euler characteristic of the thing you started with. And actually, the more punctured pieces you have, the more disks you're going to have to use to cap off those punctures. So it has to be at least 2, and as soon as you start having things with 3 or more punctures, you have to have at least 3 disks.
Great, thanks.
Can you explain what Monke's almost complex structure is?
Yeah.
You're just being very mysterious. It's a special one, but what is it?
So it's roughly speaking, the one you take the flat metric on the torus, right? So take the double cover of the Klein bottle. You take the flat metric on the torus, and that will allow you to construct, right? So when you have a metric on a manifold, that will allow you to construct a natural, almost complex structure on the cotangent bundle. And that's not the one you use, because that is not actually suitable for neck stretching. But it does have this nice property that, so you know exactly what the holomorphic cylinders for that guy are. So if you have a geodesic on your Klein bottle, it turns out that will lift to give you a cylinder in a unique way for that particular almost complex structure. And then you can kind of see why you don't expect there to be a holomorphic cylinder with odd intersection through a generic point, because those will correspond to the geodesics in the odd homology class, like the core. Let me draw a picture of the Klein bottle. So here's the Klein bottle. I'm going to get this wrong. No, okay, I think that's right. Okay, so here's the Klein bottle. You've got this geodesic that goes like that, which is the core of a Möbius strip, and you've got a geodesic that goes like this, or equivalently this, which is also the core of a Möbius strip. And those are isolated geodesics that inhabit this odd homology class that sort of got odd self-intersection number. So those are the things that give you holomorphic cylinders for that almost complex structure, which is sort of isolated cylinders. Then you need to turn this into something which is suitable for neck stretching. And he does this by some kind of, what are they called? Cutoff function type of argument. So you basically flatten the almost complex structure outside of a certain region using a cutoff function. Does that make sense?
Yeah, I think so. So what curves do you have? If you don't have isolated, you don't have all the cylinders, what do you have?
Well, you have plenty of other cylinders, right? Because, I mean, let's focus on this one coming from the Riemannian geometry. So it's not quite suitable for neck stretching, but it's, it's still a nice almost complex structure. So for all these other curves, like this curve here, you do have a holomorphic cylinder. Right, that lifts to give you a holomorphic cylinder. However, the intersection number of that cylinder with the zero section is even.
Oh, I see. I see.
The
point is you have lots of cylinders, but they're in the wrong, they have the wrong intersection number.
Yeah, so there's loads of cylinders. It's actually foliated by cylinders in many different ways. In the same way, is that right? Actually, no, sorry, is that true? Yeah, no, probably that's not true. But any time you can find a geodesic on the Klein bottle, that will lift to give you a cylinder. But it's only these very isolated geodesics that give you cylinders that have the right homological intersection number with the zero section.
And just tell me, what was Monke proving with this almost complex structure? What was he
doing?
Monke
was trying to prove this, the fact that there's no null homologous Klein bottle in the 4-ball or in C2.
I see.
So it's this paper that's I forget what it's called, how to symplectically thread a Lagrangian needle or something. But I think there is some problem elsewhere in the argument where there's an SFT neck stretching type thing, but you have some tangency condition at finite time that is assumed to hold in the limit, and maybe it doesn't hold. It's sort of so there's a slight gap in the argument for that theorem. But the almost complex structure turns out to be very useful. So it's that paper.
Thanks.
Yeah, are there any other questions?
So I have a question. So
Yeah.
where did you use the assumption of lambda in the proof?
Good question. So let's go back and have a look. So if lambda is bigger than 2, then this is a very long rectangle, very not very tall. But I can always add on a bit more height until it's twice as high as it is. Sorry, twice as wide as it is high, so that it's exactly as in this picture. And then that was key in the argument because I mean, we used the areas of these guys to, you know, get control on the SFT limits, right? So at this point here, you know, to prove this claim that there's no other components, that was an area argument. And so the area used the fact that the argument used the fact that the area was twice as long as it was high. And the fact that we were using minimal area, I didn't mention this, but you know, this guy here, this vertical curve is a minimal area curve in this manifold. And we used that when I said this statement here, that there exists a UT representing this homology class for all J's. So, you know, the areas get used in all sorts of ways. If you change the areas very slightly, you lose all control over everything, right? Over the existence of this curve or of the areas of the things in the limit. As soon as you leave this situation here, you know, it becomes a lot wilder and more possible to have interesting, very small area curves in the SFT limit. Does that make sense?
Yes, thanks a lot.
Any more questions?
I have a question.
Yeah.
So there is another phenomenon that shows up when you look at the formations of the symplectic structure, and it's the following. So as you deform, you can look at any time during the deformation at which of the moment fibers are non-displaceable by Hamiltonian isotopies. And so if you are, let's say in the monotone case here, you will see this Clifford torus, and then but at any time you can look at the leading order these potentials of the moment fibers, and I think you can always find finally many of them that have some critical point in their leading order this potential. So that in practice means, in your example, that you know at any time you can draw a finite set of points in the moment polytope that somehow moves with the deformation. And I was wondering if does it put any constraints about how does it interact with the possible visible or tropical Lagrangians that you can draw? Because you see, anytime you draw, let's say, a tropical graph in the base, that will disconnect the base in a bunch of pieces, and this somehow critical moment fibers will spread out in the components in a way that is maybe constrained in somehow. So
yeah, it's a fantastic question. I honestly don't know. Yeah, it's a good question. I don't know. All I would say is that somehow with this, I'm really interested in Lagrangians that are not, you know, not guaranteed to have any nice Floer theory, right? So there's no Floer theory in this argument. So, you know, this Klein bottle doesn't have to be monotone, doesn't have to be unobstructed or anything for this to work. So, and this is why I'm kind of confident that, well, not confident, but kind of dubious that you could prove any lower bound on the genus as lambda gets large here, because these Lagrangians are potentially unobstructed, or, you know, any kind of Lagrangian will go. So there's no guarantee that it'll have any kind of nice Floer theoretic properties or interact in a nice way with the kind of generators of whatever Chi category. So while it may well, so thinking about the kind of thing you're talking about, that may well give you some kind of control on maybe unobstructed non-orientable Lagrangians. You know, I didn't make any kind of assumption about that in the statement of the conjecture, so I don't know how useful that would actually be in the end for proving this. But I don't know, maybe I'm wrong. But it's a good question. I haven't thought about where those points would sit in relation to this Lagrangian here, for example. Yeah, maybe I should stop because it's. I was going to say something else, but people have started asking questions, so maybe I should just stop there as it's 9 o'clock, or sorry, as it's 1 o'clock, or whatever time it is for you.
Okay, so well, yeah, thank you very much for the talk. So let's first thank Jonny. So you can unmute yourself and clap. So I guess the plan is we'll open up the floor for if there's any more questions. I guess there's already been quite a few, and then after that I'll turn off the recording, and then if anyone wants to stick around, we can also have like a more informal discussion if Johnny's available. So
yeah, sure.
So are there any other questions?
Yeah, I'd like to know what direction you said you were going to talk a little more. So what were you going to say, roughly?
Yeah, well, I was just going to say this is not the only theorem along these lines. There's actually a really nice theorem of Shevchishin and Smirnov that I probably should have mentioned earlier, but I kind of wanted to make sure I got the proof in before I said this. So they do answer this question about the minimal genus in a particular case. So let me just tell you what they prove, because I really like their theorem. And then I want to draw you a picture that explains where their idea is coming from. So this really belongs in the introduction to the talk. So I should have said it earlier, but so Shevchishin and Smirnov have this result that if you take the 4 ball and blow it up in 3 sub balls, so that the exceptional guys E1, E2, and E3, the exceptional curves, have areas, let's say A, B, and C, then the class, the Z mod 2 class E1 plus E2 plus E3 is represented by a Lagrangian RP2 if and only if there's these 3 inequalities that hold, which is A has to be less than B plus C, B has to be less than C plus A, and C has to be less than A plus B. Yeah. So the 3 triangle inequalities. So they have this fantastic paper that proves this. And I just want to draw you a picture, because I was drawing these tropical Lagrangians. I want to draw you a picture to convince you of this statement, but you know why this statement is believable. So here's an almost toric picture of this manifold, this blow up. Okay, so this is the blow up at 1 point. This is C, the curve E3. Here I'm going to do 2 sort of almost toric blow ups. So this distance here is maybe B, and this distance here is maybe A. And now the claim is that if you try and draw a tropical Lagrangian like this, you can do it, and the claim is this is going to be a Lagrangian RP2. So here there's going to be a Möbius strip, and this is a sort of tropical pair of pants that gets capped off by a disk here and a disk here. So this is Lagrangian RP2. But you can do it if and only if these 3 inequalities hold. So if any of these 3 breaks down, then this thing you try and draw doesn't exist. So I just wanted to illustrate, because this was kind of the motivation behind the conjecture up here, right? That at some point, as you deform the toric or almost toric structure, the tropical Lagrangian or visible Lagrangian you try and draw disappears or hits the boundary in some obscene way and becomes singular. And that's exactly the same thing happening here. So that's all I wanted to say, was somehow these toric or tropical pictures are very good for guessing somehow when these low genus Lagrangians might fail to exist. So that's all I wanted to say about that.
And so what obstruction did they find? They must have found an obstruction to say that it doesn't exist when one of these things
So it's a kind of indirect argument. So they rationally blow up, replace it with a -4 sphere, and then use constraints on rational four manifolds to rule this out. So it's that kind of argument. In the same way that this Shevchishin Nemirovsky proof about the Klein bottle in the four ball is kind of indirect. Like you either use Lefschetz vibrations or you do a Luttinger surgery and then use constraints on the four manifold itself. So rather than directly working with the Lagrangian.
Okay, thanks.
Any other questions?
Johnny, I shared with you, perhaps I'll share with everyone. I was just kind of some draft of something tropical that I think is in class 1.0 and it's just the same picture that can be fit in our Lambda. Can you?
Okay.
Let's see if it's right. I share privately with you, so perhaps I can share with everyone. Try not.
Is it in Zoom somewhere? Should I be able to see it?
Hopefully, I didn't make any embarrassing mistake.
Probably not. But
now
how would I see this?
Everyone.
Would I have to stop sharing or something?
You need to go to the chat.
Oh, how do I do that? I don't know how to do that.
Don't know how to go to the chat?
No. I can just see some faces.
So when you're sharing, if you go on the top, you should be able to access the chat.
Oh, maybe.
Go close where it stopped sharing.
I can see it. I've got it. Got it. Yeah. Okay. Okay. So let's see. Where's it gone? Okay, so I'll stop the share and I'll share this instead because I don't think I'm currently sharing this. Okay, so this is the claim. This guy.
The bottom one, the top is one in 0.0. I thought the
top
one
0.0. Okay, yeah, that's the Givental thing.
In the wrong class, but then I think this guy should do the job.
And so what genus is that?
It's intersecting once on one side and twice on the.
Yeah, it's in the right class. I agree, but then as a tropical curve, I guess it's got this weird.
Oh yes, then we need to compute the genus.
Yeah, it looks good.
Yeah.
Yeah. Okay. So that would answer that question, which is good. But still, the question I really want to know is: can you get Klein bottle in? For all. For all lambdas.
Yeah.
But,
yeah. This is like not true, but.
Indeed, but yeah, that's cool. I should have to think about this example. Yeah. Thank you very much. Yeah.
How does the part which is meeting the boundary perpendicularly get capped off?
Oh, actually, yeah. What's going on there? That's no good, is it? Because that's going to be a.
Oh, this looks like symplectic, right? No, wait.
Yeah.
Oh,
so
yes.
for symplectic curves, this is okay.
It doesn't collapse. Yes. See, I told you that there should be some. There
Excellent.
should. Yeah.
So my conjecture stands.
Not close there. Yeah. It has 3 ends. This.
I did think it was going to be easier to prove the conjecture this way than to prove it by to find a chemical example by finding a lower boundary genus. But, okay, yeah, I should have noticed that. Yeah.
Yes, that's not collapsing there. Yeah.
Yeah. So the point with these diagrams is the way the edge meets the boundary. It should be kind of slope 2 when it meets the boundary, because otherwise you'll get something that isn't a Klein bottle. Yeah. Thank you for spotting.
No,
it.
here is slope
Can you just
2.
put a
This,
no-
this
a
end is
copy of that
right.
thing in-
The top and the bottom is wrong. I
Yeah.
mean, it's just not closed, right?
Indeed, it's just got some boundary components.
Oh, yeah.
Yeah, just got some boundary components. Yeah.
So I think was somebody else saying something there.
Oh, before that issue, before the, you pointed out there was also an issue with the top and the bottom. I was going to say, couldn't you just put the thing on the left and the right as well to deal with the horizontal part?
Yeah.
If the goal is just to get some like upper bound for the genus.
Yes, because the homology class wouldn't be changed. Yeah, I guess so. Mhm. Yeah, but as you said, there is also this issue. Anyway, it's a challenge. I'm sure someone will find it. But I was playing around with it for some time, couldn't find one. But yeah, cool. Any more questions?
So maybe, yeah, so maybe I'll go ahead and turn off the recording and then
Yeah,
we
go
can
for it.
just we can have a chat.